Hello, this is a presentation on alternate geology theory based on the growing earth hypothesis about upwelling precipitate hills and mountains. What is an upwelling precipitate hill or a mountain? This is an alternate idea to how conventional theory describes the creation of hills and mountains. In this theory, hills and mountains are made by upwelling waters from deep within the earth, mantle water. They come up, these waters are saturated with minerals, and when they get to the surface they deposit these minerals, they precipitate these minerals, and they do this over, a lot of this water comes up and does it over geologic time, precipitating more and more minerals, and these minerals pile up and create hills and mountains. So that's the gist of it. Let's get on with it. Okay, so what is the motivation of this presentation? What am I trying to do here? I'm going to try and briefly describe an alternative to what I call the old growing earth theory, which was typical of the second half of the 20th century, which was to take plate tectonics and simply make small adjustments to it. The main one being just saying that yes, the mid-ocean rift mechanism is more or less correct, except there is no subduction. So on the left we have a model with two main white arrows representing mantle material going to the mid-ocean rifts, and from there the new surface material that's created at these mid-ocean rifts pushes the rest of the surface to one side as new material is created. It's something that's skirted around in conventional theory, conventional geology theory, that the mid-ocean rift mechanism tends to push the rest of the surface around. I mean, it's supposed to only be a small rift. It's supposed to only be a small rift, and in the middle of what should be thin surface plate, and yet it pushes the continents and the rest of the crust around. So, I mean, that alone, that's one thing that doesn't sit too well with me. I think it's a bit daft. The sizes of the planets here don't matter, but yeah, the point to get from the other one is that what I'm going to say in this presentation is that the idea that mid-ocean rifts are the source of most of the new surface crust, I'm going to say that is wrong, and that mid-ocean rifts aren't that important if they exist at all. I'm not sure they even exist really. There will be some rifts in the oceans, but you can more or less ignore them for the most part when you're considering growth of the crust. So on the right I'm saying it's much more uniform, it's much more spread out over the whole of the surface. Mantle material is coming up from the mantle into the crust more or less everywhere you look, and if that's the case, then we should be able to see it just by looking at any geography that happens to be outside your window. So let's get into that then. First of all, where did I get this idea from? And it started with the observation of limestone formations, in particular thinking about how they were created. Now, the conventional theory is lots of little creatures, sea creatures, all ate calcium out of the sea, out of the rocks, and then died, and the shells of these creatures piled up, and the calcium in these shells became concentrated, and over millions of years all the shells piled up, and from that you get a sedimentary rock, which is limestone. That's the conventional theory. But when I looked into this isn't what I saw. What I saw was mineral water coming out of the ground and precipitating limestone. And well, the conventional theory just seemed convoluted and well, ridiculous. It's the daftest story I ever heard, so I thought I've got to think of a better theory than this. And you know, I was just saying what I saw I was just saying what the photos were showing, which is just mineral water coming out of the ground and precipitating limestone. I mean, who needs a better and simpler theory than that? You know, just say what you see. You couldn't ask for anything more simple. And here's a picture to illustrate this. Here's a picture of Fly Geyser in America. This is exactly what it looks like. There's mineral water coming out of the ground, and the mineral water is depositing limestone. The limestone is yellow. The green colour is biological material on the limestone, and the red material is iron, which is of interest to us because this mineral water isn't just depositing limestone, it can deposit other minerals, and we're going to say that this is mantle water, so it's got all sorts of minerals in it, so you can get all sorts of rocks from it. But what you see here, this Fly Geyser, is representative of pretty much all hills and all mountains, in that it's mantle water coming up and depositing minerals by precipitation. And here's a picture from Turkey, I believe, and it's pretty much the same thing, apart from the formation's far bigger, so you can't actually see a kind of mound of with water coming out the top. What you've got is an enormous landscape made by a mineral spring that is just pouring out mineral water, and the mineral water is precipitating limestone, so you end up with this enormous landscape of limestone. And you can just imagine, you can see the limestone takes on the sort of formation of as exactly how you'd expect it would if it was coming out of a spring and pouring down a hillside. You just get this kind of pouring, a frozen waterfall kind of look about it, and that's exactly what you'd expect if the mineral spring theory is correct. So I want to look at primarily layered hills and mountains, for which case conventional theory consistently asserts these layered hills are sedimentary. So let's just briefly look at conventional sedimentary theory for such hills. On the left, it's a depiction of geological layers that have been laid down by sedimentation, and then over geologic time these layers get worn away, and then you're left with these mountains and hills that have these easy to see layers with a bit of the silt in the valley from the erosion of the hills. So that's simple enough. And on the right is the volcano, the conventional volcano or volcano-like object, where again you start with it's that the volcano piles up the layers and then erosion removes a bit of the layers. So that's just a rough template of what conventional theory says is the origin of the layered hills and mountains that we're going to be looking at. So the first picture we'll look at is this photo of the Grand Canyon. An overview of it is a load of red Grand Canyon rocks, multi-layered, and at the top of the red layering there is this yellowish white layering, which is in the foreground. So you've got red rocks and a white top layer, but in the middle of the picture you've got the object of interest, which is what looks to be a red rock, but it's covered in grey stuff. So the question is, where is that grey stuff coming from? Where is it coming from? And you've got to try and answer that within conventional theory. All you do is you start at the bottom of the canyon, and the grey matter's down there in the middle, and you work your way up the layers, and you can still see the grey matter, so you know it's coming from somewhere higher. And you go higher and higher, and you actually find that the grey matter is on the top of the central object. And so you have to sort of think, okay, maybe that's where it all came from, unless you're going to hypothesize that the wind blew that fine dusting of grey matter up there. So, you know, to answer the question, it's probably, a conventional theory might say it's the it used to sit on the top of this central object, and then it's all sort of fallen off, eroded away, quite simply. One problem with that is if you look around the other cliffs, the grey matter goes part way up those cliffs, and then stops at a certain level. And you know, you have to ask, well, how has it got up the side of these other cliffs if it used to sit on top of the central column? I mean, the central object. Has the wind blown it up there? Well, that seems unlikely, considering it's evenly distributed around, you know, around the whole central column. All the scree slopes seem to be equally have equal amounts of deposits of this grey material. So, I mean, that fact does not sit well with the idea that this grey stuff sat on top of the central column, the central object. But also, if this grey stuff did sit on top of the central object, why isn't there a corresponding grey layer in all the surrounding red rocks? Because to get to anything that resembles the grey layer, you have to go much higher, up to the sort of white yellow gypsumy layer, and this central object isn't high enough for that. So it doesn't look, to me, it doesn't look like conventional theory can really explain the grey material very well. And so my alternative theory is that this central object is actively extruding, expelling new grey material into the Grand Canyon. And this grey material is coming up from the mantle and then leaking out before it gets to the top of the top layers of the Grand Canyon. In fact, you can more or less make out how far it gets before it leaks out onto the surface. So this is evidence that favours the upwelling mineral seep theory, and well, I'm sure conventional theorists have found a way to explain it, but their explanation will be more convoluted, more complicated. And Occam's razor says take the simpler solution. Next up, let's look at this hill in petrified forest it's called the Petrified Forest in America. It's a layered hill. This is soft material. The hill's made of soft material. And the most noteworthy thing is, while it has horizontal layers, it's quite evident that the top is apparently eroding, and there is material coming down off the sides of the hill from the top, and it's creating mud slopes down the side, and these cut across the horizontal layers. At a first glance, you might think, well, what's wrong with this? This is in line with standard theory, isn't it? The top's eroding, the hill is eroding, as standard theory says, because it's an eroding relic, an eroding sedimentary relic from the past. Well, yes, but if the top is eroding, why aren't the sides eroding just as much? I mean, if you argue that, oh, the top is softer, therefore it erodes faster, well, the top should have eroded. In that case, the top should have eroded a long time ago. But it's still here, and then you've got that outcrop again that is quite common in these situations where there's a lot of hard rock at the top. There is some hard rock at the top. However, the alternate theory, the upwelling seep theory, suggests that this is an active feature. The material coming out at the top and coming down the side isn't really eroding away. It's coming out the top, going down the side, and then this is becoming a new permanent part of the hill. It's going to, the mud is going to, or the mud or the silt or whatever you want to call it, is going down the side and gluing and sort of gluing itself to the side of the hill. So the hill is getting bigger. This and what you are seeing is a hill growing. Now there's more to say about this. Somebody would object that if that was the case, then these stripes, these horizontal stripes, you wouldn't be able to see them because of all this stuff going down the side. The whole thing would have been covered up a long time ago, so surely this stuff going off the top is going down the top and then getting washed away, so that we can still see these stripes. And that's a good point if that's what you've thought, and it needs addressing. So this is a complication in my theory, in upwelling precipitate theory, and I have to address it by complicating my theory, but I think it's worth looking at, so we'll do that next. So I've got to explain why if the hill is producing new stuff coming out the top that's pouring down the side, why isn't this new stuff covering up the old stripes? And why can we still see the new stripes if the new stuff isn't coming down the side and then not blowing off? It should pile up, it should cover the stripes. So how am I going to do this? Am I going to use a new mad idea? No, I'm going to use an already existing idea in geology. That idea is, it's a concept that geologists are already aware of and use and accept, and they apply it. They use it when faced with certain kinds of rings that they find in geology, find in rocks, and they call them Lysiang rings or Lysiang rings. Yeah, I don't know if I'm pronouncing that correctly, but what they are is they are shapes in rocks that geologists correctly believe to my mind, are caused by water running through the rock. And here's a picture of some Lysiang rings. I just call them water rings. I prefer terms that are self-explanatory. So so water's flown through this rock and it's shaped the rock. It's shaped the patterns in the rock as the water's gone through. So the water can craft rocks as the water goes through the rocks, and that to me is a appealing idea. It makes sense, but it's also very powerful. So I want to apply that idea to the hill. So the power of this Lysiang watering concept is that it's a reinforcing, continuous way of shaping and crafting rocks. So it doesn't just apply once at deposition and then the ravages of geology alter the rock in other ways. No, this water rings continue to reinforce their own patterns. So when you've got a hill being created, as I'm asserting with these clay hills and stuff, if these water forces are in action, then they will reinforce, they will continue to maintain the patterns that they are currently creating. So as new mud comes down the side of a hill, it too will be affected by these water Lysiang ring effects, and they too will take on the rings and the effects of the Lysiang water effects and stuff. So they will take on these horizontal lines as if they were part of the pre-existing rock. But the new material can be affected by this, and so new material that's added gets these horizontal stripes, and then geologists come along and think, oh, the horizontal stripe bit is the old bit, and the new stuff coming down is separate from that, and you don't confuse the two. Well, I think the two are one and the same because it's new material, that will become part of the hill. Now let's have a look at another image. Another way to look at this is, let me just see, is this density stack, liquid density stack. So you've got all these different liquids with different density, and this is similar to lysogang rings. Certainly not the same, but it's similar in that liquids will sort themselves out and put themselves into different layers. And this applies in a situation where it's only the liquids, but if you were to put these liquids in a medium, such as rock, such as in a porous rock, you get exactly the same effect. So, you know, when you look at a rock and there's all these different layers in the rock, you shouldn't immediately think, oh, that's ancient deposition, because it can be lysogang rings, and it can be this effect, which is a similar sort of effect of liquids. And you know, the overall assertion of water coming up from the mantle, water saturated in many different minerals, then these minerals will sort themselves out into layers. If you look at the formations I'm looking at, you know, you can see layers, and then there's gaps in between layers, and you think, oh, well, that's not quite the same as this liquid density stack that we've got here. Well, it might be. The layers in between, the bits in between layers where there doesn't seem to be any particular colouring, that might just be a mineral that doesn't have a particular colour. I think an effect like this is in effect on these hills, and this is what's creating the lines. But it's, you know, geologists have never looked into this, as far as I can tell. I think there's potential. There's potential to do investigations into this, simple, cheap investigations, and I'll explain that with an example. So, as a possible experiment to verify or vindicate or evidence my idea, my lysogang idea for hills, use this picture of the desert to use this image to imagine dumping a load of clay on some flat ground somewhere, and at the base of the clay there being a load of water-soluble minerals like rust, like salt, and a few other minerals. I'll have to look into which ones we can use. But yeah, the clay is dumped onto the ground, and at the foot of it, at the foot of the hill, it'll start soaking up all these minerals. And according to my amazing theory, these minerals will soak up into the clay, and they won't just spread out and diffuse, they'll actually form layers like the ones you see in this hill. And that will completely verify my theory and be a big discredit to the existing top-down deposition theory. I should point out that there's plenty of cases in geology where top-down deposition is exactly what's happening, but it's a mistake to assume that all sort of nice flat layers are by top-down deposition. So that's one of the sort of knee-jerk reactions I get when I say, you know, look at these flat layers. I don't think they're top-down deposition. I think it's water effects doing this, and I think that's. And the people always say to me, "Oh, you're crazy because look at this, this, and this. These are clearly top-down depositions, and so you're mad." And I say, well, to that I say, yes, there are some very clear-cut cases of top-down deposition. I just want to. I don't want to take all those away from you. I just want to point out that not all of them are. Some of them are these lysogang water effects. So there you go. Okay, so for this image of a rock outcrop, I only want to make one simple point, and that is the material coming off the outcrop is coming off in a fine powder, as silt, and it's coming off in quite a large amount. And this runs contrary to the sort of old story we get when we learn geology at school, which is rocks erode by first large chunks breaking off of an outcrop, and then the chunks roll down the valley over geologic time very slowly. Then they go into a river, and slowly they get washed down the river and into the sea. And it takes all this and standard, and what we get taught in school is that it takes all this time of going from the scree slope down the hill, down the river, down the sea, to break up these boulders, to break up the rock, which starts as boulders. It's broken down into rocks, then the rocks get broken down into pebbles, smaller pebbles, and the pebbles get broken into sand grains, smaller and smaller, until it's a fine powder, and then that's the stuff that makes up the new sedimentary layer. Well, this image and loads of them, it's just standard that that's not the case at all. It's this stuff, silt and things that comes off the rock outcrop is usually a fine powder as soon as it leaves the rock. So this is a significant factor, and it should be, while standard theory totally accommodates this, I do think they've kind of got it, they quietly get it the wrong way around, in that they assume that the boulder to rocks to pebbles to sand to dust is the standard procedure, and the fine silt straight from the rock outcrop is the exception. Well, I say no, it's usually silt straight from the rock outcrop which is normal. And this, you can build on this. This, I think, supports the theory of upwelling seep and sort of mineral excretion from rock faces. So it's worth keeping in mind. So yes, we're on to a favourite one of mine. This is one I keep coming back to. It's a picture of somewhere in America where the amount of silt coming off the outcrop is, to my mind, completely disproportionate to the size of the outcrop. You've got this small spindle of an outcrop, and you've got this vast amount of clay sliding down the hill, both on the small feature on the left, and also in the background. The amount of clay just seems to be just disproportionate to the underlying rock. So what does this mean, and how does convention explain it? Well, all this silt was supposed to be above the outcrop. It's the top layer. You can actually see a top hat of what I call a top hat of silt or clay stuck on top of the spire on the left. I've seen close-ups of this of the spire, and that the top stuff is the same material as the scree slope. One way conventional geology explains it is that the whole structure is just eroding very quickly, and so it's eroding quickly and everything's just falling away very quickly. So if that's true, then we have to assume we've got quite lucky there, that we're just seeing this snapshot of the whole outcrop collapsing, and now there's just that tiny spire left, and maybe in 1,000 years or so that spire will be gone as well, and all you'll be left with is a pile of mud, a pile of clay, with no sign of the outcrop. So we're lucky, because we just get to see the spire just before it dies. Well, the thing is, occasionally you are going to get, that makes sense in a way, you are going to get lucky and see these spires occasionally, but what you find is when you look around at other features, we tend to get lucky all the time. Another popular one I like to look at is factory butt. That's somewhere in America as well, and that's a huge amount of silt and clay coming off a relatively small outcrop. And again, conventional geology just says, oh, we got lucky, in a few tens of thousands of years the whole thing is going to be gone, but we're lucky and we're just seeing the last of the outcrop before it all collapses. And this just happens time and time again. We're getting lucky, so you know, you could work the probability, and if you do the maths, and you'd be able to show that, you know, this is just unrealistic, and that's something to look into. But that's what I assert at the moment, that the luck that you need to get all these snapshots of these outcrops just before they die with the immense amount of scree coming off them. I assert that it's that alone can show that conventional geology is wrong about this. What else? What else is there? Well, and the other thing is, okay, if we do assume that this is conventional geology is right and this thing really is collapsing quickly, well, where is all the hard rock that's collapsed? How come we can only see the top layer? You can see all that, but the bottom layer, there's no harder rocks in all the scree. It's just missing. So conventional geology is missing a huge piece of the evidence that it requires, and everybody just seems to look the other way. Well, I'm saying no, I need to see the rest of the formation that's collapsed. So this to me is a very striking example, a very striking counterexample to what conventional geology requires. So what's the alternative? Well, again, the alternative is that these outcrops are mineral fountains where upwelling mineral waters from the mantle are getting to the surface and then precipitating tons of soft minerals at the surface. And this is what we're seeing. It's a mineral spring in a way. So the soft clay just pours out of these features like a fountain, and so that's how you end up with these immense amounts of clay just pouring out of these features, that intuitively are far too small to create these vast amounts of erosion and scree. So I think I'm going to keep coming back to this example in future. Yeah. Also, in my assertion is that top hat is quite newly created. If somebody was to go up there and knock and brush off all the clay and scree on top of that outcrop, then I assert within years a new hat will start to form. Not because the wind's blowing it up there, but because new minerals are coming out of the top. So that's an experiment I'd like to see done. I just need a ticket to America and a workman's brush, and then I can get on with it. But anybody in America listening to this, they can just drive the car over there and brush it off, and we'll see the real results in a few years. Here we've got a rock outcrop with material coming off of it. So the rock outcrop looks to be mostly grey, but the material coming out of it is orange, dark orange. So it could be, the rock type could be anything. I'll assume it's gneiss or schist for the time being, but it's obviously not gneiss or schist scree that's coming out of the rock. It's rust. It's iron oxide. So and I like how the iron oxide just seems to be pouring out like little rivers. So I don't know what convention says about this. Was there an iron oxide layer just on top of this grey rock layer? That is, we've just caught the last end of it. We've got lucky and we're just seeing the last of the iron oxide pouring off the top of the hill. But the upwelling mantle mineral water idea is quite clear about what's happening here. It is a grey, whatever rock type the outcrop is made of, it is now experiencing upwelling mantle waters that have different minerals in them. So you've got one rock type secreting a different rock type. It's the sort of thing that conventional theory is going to struggle to explain, but is trivial to explain using upwelling mantle mineral water theory. So I like that picture. This is Sheep Rock in Oregon, America, and this is what now should be a familiar case. One very similar to the others that we've been looking at. We've got it's a hill with an outcrop at the top, and a silt or scree running from the top down to the bottom of the formation, and there's a lot of it. The scree itself isn't actually orange. That's the colour of the dead grass that's growing on the scree. So what can be said about this? What does conventional theory say about it, and what does upwelling mantle mineral waters theory say about it? Well, what I like about it is the overall look of it. It just looks like a volcano, really. The scree running from the top looks like lava, flowing quite rapidly down the side of the hill in all directions. But it does sort of give an overall impression of a dynamic system. And the scree runs right from the top of the hill right under the outcrop. So, you know, according to conventional theory, we've got lucky again in that the last of the scree is about to leave the top, and then that's it, there'll be no more. Unless you want to say it's the outcrop at the top that's creating the scree, in which case, just looking around, there's a heck of a lot of it. There's a heck of a lot of scree for just a small outcrop, so that outcrop's eroding away very quickly. So we've got a lucky snapshot again. So a bit of a unknown in this is what colour is the or what mineral type is the scree made out of, because if it's the same stuff as the white cliffs, white rocks, then you've got to ask why isn't the grass growing on the white rocks as well? I don't know. So I don't think there's anything new here. It's just a visually aesthetic illustration of the points I've already made, and just another example that I'd say supports upwelling mantle mineral water theory. This one is interesting to me. We've got a sea cliff here, and there's a lot of scree and silt coming off of it. It's quite dramatic, I'd say, the amount of scree coming off, and the angle of the scree is a steep angle, which indicates it's coming off quickly. So what does conventional theory say about it? It says conventional theory would say it's the sea cliffs eroding into the sea, and there is a little bit of evidence in support of that, in that there are two old scree slopes that are further out into towards the sea, that have stopped piling up, and there's ones behind them. So it's easy for a conventional theorist, it's easy for a conventional geologist to say, look, the sea cliff is retreating, so this supports the idea. So this supports conventional idea of sea cliff erosion. Well, yes, I would give them that, but I wouldn't say it's 100%. I think those outposts could have been created with the sea cliff more or less in the same position it is now, but the scree channels might have just become cut off. So the sea cliff's in the same position now, but the scree channels changed, so the scree started falling down some other place. So those old big ones just stopped getting fed, so now they're disintegrating. So I'd consider that possibility. I'd consider arguing that possibility, but I'm open-minded about that. But that's not the main point. That's not a vital point of what I'm going to try and say. The next thing to note is just the enormous amount of scree coming off the cliff. It's just vast. It's the amount of scree is a large percentage of the cliff face, really, the amount. So that's quite dramatic. Another thing to note is that how it all seems to get funneled nicely down. How is it doing that? I mean, it's a whole face, isn't it? So how is it all getting funneled into these channels? So that's kind of a count against the whole face eroding. Here's a point that I could have made on other things, but I think it's good to make on this one. Good to make on this picture is, if we're assuming that it's wind and rain eroding these cliffs, these outcrops, then if it's wind and it's blowing off specks of dust, like we see here, because the silt is basically specks of a big accumulation of specks of dust. If it's wind blowing off specks of dust, then why isn't the wind blowing the specks of dust off, into the distance or into the sea? Why is it blowing the cliff? Why is the wind blowing the cliff just enough that it dislodges a speck of dust, and then the speck of dust falls downwards, as if the wind doesn't exist? So, to me that doesn't look like wind erosion. And if it's rain erosion, we're just getting the sea cliff wet, and that's enough to turn it to dust. It doesn't seem too likely to me, but let's just suppose it's true. Then why can't the same water, why can't the same rain erode away these scree piles? Because the scree piles are looser and should be easier to erode away themselves. So you've got the rain, which is supposed to be really good at eroding away the sea cliff, but it can't erode away the scree slopes. And what's more, and perhaps even more striking, is you've got the sea. And twice a day the sea comes along and is supposed to erode away the scree slopes, and yet you can look at the base of the scree slopes and, well, they're hardly touched by the sea. So this idea that water's eroding away the sea cliff at any great rate, at a comparable rate to the scree slope deposition, it just doesn't, it's implausible. It makes no sense. The scree is falling faster than the sea can erode away the base of the scree slopes. So how can the sea be eroding away the sea cliffs when it can't even make a dent on the scree slopes? It's self-contradicting. I mean, at this point, conventional theory can actually make a suggestion that I completely agree with. You could say a conventional theory could stay well within conventional theory and say that these scree piles are not a sea cliff erosion. They are underground rivers. They're coming from underground rivers. All this scree is the end point and result of underground rivers pouring out silt from inland. And to that I'd agree. I'd say that's much closer to what's actually happening. The only difference between me and them at that point, on this point, would be, I'd say the new mineral is coming from deep underground, from the mantle, while they'll say it's shifting land soil to the seaside. And maybe we could be more or less in agreement here. I could be in agreement with the convention. I could be in agreement with conventional geologists. But the strong point I'd make here, if that's the case, if that's what we're going with, is that this idea of internal water supplies creating all this scree should not be taken as an exceptional case. That can be applied to the sea cliff, but nowhere else. I would want to sort of impress on them yes, you can have that, but we should also take this and apply it to all the other examples I've given you just now, such as the hills inland. So, you know, this picture could be a way of getting conventional geologists on board with my idea, really. Yeah, so what a good illustrative picture. Wonder how many other geologists and how many geology students could have these ideas about these pictures. Am I the only person who thinks these thoughts? So we're coming to near the end of the pictures that I want to look at. This is one of the last ones. Here we've got a mountain. A mountain that has very striking vertical seams, and this is a mountain that me and conventional geologists would strongly disagree on. Conventional geologists would say this is a mountain composed of a sedimentary formation that has been tilted 90 degrees, whereas upwelling mantle mineral water theory asserts it's got nothing to do with ancient sedimentary layers. It's an active, and currently the layers are not sedimentary, they are upwelling seep channels or seep conduits, and minerals and water are going upwards in the direction of those seams. So how would we start to discern which theory is correct? Well, I'd point again I'd look at the silt and scree coming off of the mountain, and one simple observation is the colour of the silt, and it's orange, and yet the mountain is both orange and black. So that just suggests to me that the orange seams are the active ones. This is it's iron oxide that's migrating to the top of the mountain. You know, this could be. We could have asked in one of the previous slides, one of the previous pictures. You know, whether the iron oxide mountain that was secreting iron oxide at the top of the mountain. We could have asked, right, what happens if we chop this mountain in half? What would we see? Well, I think we'd see something like this. The iron oxide is migrating upwards, up through the mountain, coming out at the top. So you've got these conduits of upwelling mantle mineral water, and because they're active, they are pouring out, they are precipitating out minerals and scree and dust. Whereas the black rock, that is older rock, and it's not active compared to the iron oxide seams. So the scree gives away which of the seams are active, and conventional theory would just call me an idiot for even thinking about this. They'd just say, oh, it's eroding away, but they wouldn't quite be able to, you know, they'd have to have a reason for why it's the iron oxide that's seeping out, and yet the black material isn't as prevalent in the scree and dust. Anyway, I'm sure, like I say, conventional theory has an explanation for all this, but when you're contemplating upwelling mantle mineral water theory, you can see that this theory is consistent with observations. You know, this is exactly what you'd expect if upwelling mantle mineral theory was correct. So it's you know, despite this photograph being low resolution, I think this is a good illustrative photo, and I wanted to include it. Okay, so we'll briefly look at a few more pictures. This one is Bear Hill, somewhere in America, I think. It has features that I consider typical of a upwelling mantle mineral water feature, which is vast amounts of scree and silt coming off of it. I don't think wind and rain can create this kind of erosion. I don't think there was ancient sedimentary layers that were much higher than the land is today, and that they've all gone, apart from one or two of these hills that are just remaining, and in a few 100,000 years they're going to be gone. I think it's an active feature, and the hill itself, if it isn't growing, it's at least replenishing itself with new material coming up from the mantle every day. So when you see something like this, I think I'd always assume it's an upwelling mantle mineral feature. So let's just ask a quick and simple question. If these hills and mountains are indeed upwelling mantle mineral water features, how do they start? How do they begin? What do they look like then? And the simple answer is they just look like mud mounds with water coming out the top, like little miniature what are known as mud plumes. And there's quite a few examples of those around the world. These are in Trinidad and Tobago at Devil's Wood Yard. So they're kind of self-descriptive, exactly what you see. It's just water coming up from the underground and precipitating water and mud. Conventional theory will say it's water being circulated around the crust, whereas I'd say it's water coming up from the mantle. Conventional geologists would say it's material just being recycled around the crust, and I say no, this is new silt and sand coming up from the mantle. So, you know, we've got the same data, it's just different interpretations. Here's another simple question. What do upwelling mantle mineral water features look like once the water stops upwelling? And I'd say this is what they look like. It's a rock outcrop, but it has very little, or certainly relatively very little, scree and silt coming off of it compared to the features that we've been looking at. So when the water stops upwelling, it stops upwelling minerals. The minerals stop precipitating out of the outcrop, and then real erosion, the wind and rain, does actually blow most of the silt away, and you're left with this naked rock feature. Pretty good, eh? It all makes sense to me. So finally, I just want to make the point that I don't think my idea is radical at all. I think this is a normal, simple idea that we're all introduced to as small children when we get these magic crystal trees. There's no high-level tricks here, it's just simple ideas that children can understand, and that science is fully aware of and considers no special action. It should be perfectly common in nature. And just consider what the growing earth philosophy is. The earth is growing, the mantle is producing new material, or there's new material getting inside the earth, and the whole earth is growing by about 2 centimeters a year. And you know, most people think it's expanding in the mid-oceans. Well, if the crust is being pushed out by 2 centimeters every year, then it must be cracking. If it's cracking, then that allows material to get in between the cracks. And what do we know about the mantle? It's got water in it, it's got minerals in it. You know, that mantle is going to be squashed upwards by the force of the growth force of the earth. So these cracks are going to fill in with new minerals and water, and the crust is going to be quite saturated in water, so these upwelling minerals are going to come up through the crust pretty much everywhere you look. So, you know, I don't think it's reasonable, this idea that growth is only happening out in the mid-ocean rifts. I really think it's happening everywhere you look. When you really start to digest the upwelling mantle mineral water theory, that and you really start to see it in your mind, and when you visualize, you know, the upwelling water and the precipitation of minerals and then you go outside and you start looking at geographic features and you start trying to apply this. Geology and geography, the features that you see begin to make a lot more sense. It's geology and geography are a lot simpler than you think, because upwelling deposition, upwelling mantle minerals and the deposition of these minerals can explain a lot of things a lot easier than the conventional set of ideas of geology. So I recommend everybody sort of think about it and start trying to see it in nature. And besides anything else, I think it's a lot more, it's a lot of fun to have a new idea, so I enjoy having new ideas. So that's it really. I hope you found this video interesting, and I'll try and do some more. Thanks for watching.